you're less, less shy to ask those questions that you might want to ask in class. You can ask them for your tutor. So that should be helpful. Definitely encourage you to try it out. All right, anything that you need me to clarify as far as the tutoring goes, or any other quick general questions you may have before we start on 2.5?
Are we going to go over the quiz?
In general, I don't go over quizzes during class time. If there are specific questions, then you guys can ask me through Canvas, and I'll try to reply to those individual people. I know that there were already some questions with regards to input for the quiz, and I am going to first, reply to you in Canvas and keep the conversation there, and then decide what to do with it. So one of the, I can't say it was common, so I have 3 classes. Each class is about 40 people, so it's 120 people. And from 120 people, probably about 5 people had this issue that, for the quiz, they would input when the equation was solved or when something had to be done, instead of putting in just 2 for the box, they would put in x equals 2 or something of that nature, where the input wouldn't correspond to what the program was anticipating. My main concern is that the homework questions were the same. The homework questions were exactly the same format, the same input. So if you would have done your homework, you would have ran into those issues earlier during your homework and fixed them, because you would be seeing error messages and saying you're not getting the right answer. Whereas if you didn't do your homework and for the first time you try to do it during the quiz, then you might have those input issues. But my thing is, if that's the case and you didn't do your homework, then I'm not going to be correcting anything on the quiz. But if there are some other issues, then I am willing to take a look at them. So I'll have to first respond to your Canvas messages and see what the issues are. But I don't just go over the quiz for the entire class. I would do it for people that ask. And if a lot of people ask, then I might do a quick write-up and just post it to the files on Canvas and announce it that way. All right. So then let's go ahead and get started. Our 2.5 lesson is a graphing lesson. And for graphing purposes, I have a different program that I'm going to use. So let me start that up and share that part. Overall, it's a nice program. It only has advantages except one area. The disadvantage is when I upload this file, and I don't know how many of you actually even look through the files I upload, but when I upload this file, it is not page by page. It is instead like a large file that you have to zoom in on the parts that you're interested in. And if I don't make the file too large or too lengthy, then usually it's fine and you can see everything okay. So you'll have to let me know if you're able to see it or if I'll need to do something about it. But this is the software I'll be using for 2.5, which deals with transformations. Transformations of functions and how to graph. So before, and in algebra, oftentimes when we would graph, is we would just get some ordered pairs. We would plot them, and then we would try to find a pattern. And then kind of continue on with that pattern and say, this is our graph. That's what we did in algebra. But we already did more extensive and more specific graphing for things like parabolas, mostly. When we would graph parabolas, we would say quadratic function, or parabola is the graph of a quadratic function. We would start by graphing the sort of parent function, or the basic case of a parabola, f of x equals x squared. And we usually started it by plotting some points, but at this point we already know what the graph looks like. So I'm just going to go ahead and graph it here. On our coordinate plane, we would have 0, 0, 1, 1, 2, 4, 3, 9, and negative 1 would still be 1, negative 2 would still be 4, negative 3 would still be 9. And when we connect these with a nice smooth curve, the resulting graph is that of a parabola, one of our functions that we found in the library of functions in 2.4. And in algebra, we also graphed a few different variations of these parabolas. For example, if we graphed something like x squared plus 2, we would probably start noticing certain patterns. If I were to graph x squared plus 2 without writing out where the points are coming from, we hopefully can do it mentally. If I now plug in 0, I would get 0 squared plus 2, which is 2. If I plug in 1, 1 squared plus 2, that's 3. Negative 1 also is 3. 2 squared is 4. 4 plus 2 is 6. Negative 2, same thing. And if I connected these points, I would see that the resulting shape is still a parabola, and it is related to the previous parabola by saying, well, all of my points are now shifted up 2 units. So what this plus 2 did is it moved all the points 2 units up, and that gave me the resulting graph. So these types of patterns is what we're going to explore in today's lesson. For example, if we were to graph f of x equals x minus 5 squared, we would notice that the points we would get are shifted 5 units to the right. Because now if I plug in 5 for my x, my resulting value would be 0. So I would have a 0.50, which would be here. If I plug in 6, I would get 1. If I plug in 4, I would get 1. And we would then notice that all of my points were shifted 5 units to the right. And we would take note of that, and we would again say, well, let's generalize this and let's use it for general type of functions, not necessarily just x squared, but any of the parent functions from our library to help us graph various transformations. So all the points would get moved 5 units. So this guy would go 1, 2, 3, 4, 5. Let's keep it green. 1, 4, 5. This guy would also go 1, 2, 3, 4, 5. And we would see that again, our general parabola would maintain its shape, but all the points would be 5 units over to the right. And those are the patterns we would notice. This guy was 2 units up. This was 5 units right. And then we'll explore a few other transformations as well. So let's start with the first two transformations that are the vertical and the horizontal shifts. Vertical shift first. For vertical shift, we will use k to represent the shift, and k is going to be a positive value. K is greater than 0. And the graph of y equals f of x plus k, where f of x is our parent function from the library of functions that we've established, is going to be a graph of f of x, which is shifted k units up. So plus k is outside of the function. That's k units up. And if we have f of x minus k, then that will be the graph of f of x moved k units down, as we can see on this example over here. We had x squared plus 2, so we had the graph moved 2 units up. So that was the vertical shift. Horizontal shift, we will use the letter h to represent horizontal shift. Again, h is a positive value. So if we have y equals f of x minus h, this will be a shift horizontally h units to the right. And if we have y equals f of x plus h, this is again shift horizontally h units to the left. So notice the difference. Notice that for up and down, plus was up, minus was down. However, for left and right, minus inside the function is right, plus inside the function is left. So it's the opposite of what you would expect. But we've already encountered these when we were graphing circles. We saw that for circles, if we had a circle centered, for example, at positive 2, negative 3, it would look like that with a radius of 3, for example, right? So we know, so if we had a circle with this equation, the center of this circle would actually be positive 2, negative 3. So we would use the opposite of whatever is inside the function. So we've already seen these. Let me see if I can erase it. There we go. So again, horizontal shift, make sure you guys pay attention to it. It's the opposite of whatever is inside your function. So if we apply both of these at the same time, let's call this number 1. Let's say we want to graph h of x equals, and let's refresh our memory on absolute value. So if we have absolute value of x plus 3 plus 2, that will be our h of x function. And from now on, we are not going to just plug in some ordered pairs, or rather find some ordered pairs. We're not going to use that approach. We're going to use transformations in order to graph it. Even though the graph would be the same, of course, whichever method I use, the graph would not change. The reason why we prefer to use transformations is because at some point this semester, when we get to trig and we start graphing trig functions, we will have a pretty easy way of graphing the parent function like sine or cosine. But when we encounter different transformations and we see something like negative 3 cosine of 2 pi x minus pi over 6, we don't want to sit there and plot a bunch of points. We want to instead say, all right, I know what this negative 3 does, I know what this coefficient does, and I know what this minus pi over 6 does, or maybe even plus 3 out there. We want to recognize these transformations regardless of what our parent function is, and then apply them, and that'll be a much quicker approach. So that's why we definitely want to be able to apply the transformations as opposed to plugging in points. And the trick for applying transformations is to start with a parent function. In this case, let's call it f of x for our parent function. It would be the absolute value function. So f of x is absolute value of x. And then through a bunch of steps or a couple of steps, we want to arrive at this new function, which in our case is h of x, the absolute value of x plus 3 inside, plus 3 is inside, and then plus 2 is outside. So in order to keep track of the steps, what you want to do is you want to start with the parent function, and then you want to say, let's either replace x with something or add something to the entire function that we have. For example, here, it doesn't matter whether I first choose to add 2 to the function and then replace x with x plus 3, right? It would be the same final version. But when we learn more transformations, you will see that if you do one transformation before the other, it does affect and it does give you a different result. So you want to keep your transformations in such order that it gives you the proper function in the end. And in general, the vertical shift, this plus 2, is always going to be the very last one that you should apply. Sometimes it doesn't matter, but when it does, you want it to be the last one. So you'll start getting used to that. Our first step here will be to replace x with x plus 3. And then this is our now new function with x plus 3 inside the absolute value. And then we want to add 2 to this new function, which will be outside. So that gives us the function that we are after, which is h of x. Let's do blue for that, which gives us this guy that we were trying to graph, and also describes the steps that we need to take. So the first step, plus 3 inside the function, that'll tell me to go 3 units left. And the plus 2 outside of the function will tell me that to those points that I've already shifted 3 units to the left, I should now move them 2 units up. So 3 left and 2 up is the correct transformation. And again, in this case, you could do both of these at the same step, or you could do either one first. It wouldn't really matter, but there are going to be cases and examples where it does matter. So in general, I'm going to say, put a little note, vertical shift should be applied last. That's all we're going to say on that. All right, so let's see how this graph would look. The book will tell you to use at least 3 points. And I think 3 points is enough as long as you remember the general shape of your functions. Our parent function, f of x equals absolute value of x, I know is a V shape that does that, right? It's a V shape. Connected at the vertex. And you don't even have to actually graph the parent function. You can just keep the points from the parent function. Kind of missed. Let's try again. Close enough. Oops. Just make this guy bigger. All right, so this would be the parent function, f of x equals absolute value of x. But it's important that you keep track of at least 3 points, because those points you will move around and then you'll get your final result. So here I will do it as 2 separate steps, even though we could do it as 1 step. So first I'm going to do the 3 to the left. So each point gets moved 3 units to the left. That would be the first transformation. And second, I'm going to do the 2 units up. So each point goes up 2 units. And those were the only transformations I had. So that is my final result here. I maintain my V shape for my absolute value function. Connect these points. And this is it. So again, only the blue part is what you need to know what you need to have on the graph. The rest are sort of intermediate steps. So that way you can at least kind of keep track of what has been done. And if you're doing it on paper, I definitely encourage you to use maybe different colors, because it could get pretty tricky, especially when you start doing reflections as well. So that would be one of our questions. Let me give you an example to try on your own, and we'll do a different parent function. Let's call this number 2. Let's call it g of x equals, let's do a square root of x minus 3. And which one do we have here? We had plus 3, so yeah, minus 3. And this will be minus 4. And the square root ends here, of course. So take 5 minutes, and again, using transformations, go ahead and graph this g of x, and then we'll go over it. Okay. So again, when we're just introducing these, and there's only two of them, it's pretty straightforward, but it does get a little more challenging. Our parent function here is the square root function. And the transformations that we do, we will first change x, or replace x with x minus 3, and then we will subtract 4 from this new, minus 3 here, and then we will subtract 4 from this new function. So the first transformation tells me 3 units to the right, and the second transformation will tell me 4 units down. But again, if you only have these two shifts, then you can apply them at the same step. That would be perfectly okay. So let's grab this one. All right, so the parent function, square root of x, if you forget what any of them look like, just plot some points. 3, 4, 5 points should be enough to get the graph. And we know that square root of 0 is 0. We know that square root of 1 is 1. Square root of 4 is 2. And we could also do 9. So 4, 5, 6, 7, 8, 9. Square root of 9 is 3. If you want, connect the points for the parent. If you don't want to, just keep the points. So I'd probably just keep the points. See if I can undo this. There we go. So I'll just keep the points there because it's less messy that way. Then I have my transformations. Again, minus 3 inside the function tells me 3 to the right. So each point is going 1, 2, 3 to the right. This guy, 1, 2, 3 to the right. This guy, and this guy. They all went 3 to the right. And then we have 4 down. So then each of the blue points is now going 4 units down. 1, 2, 3, 4. 1, 2, 3, 4. 4 units down. And my final version is this guy. Now, I know that my square root function, the parent graph, doesn't have anything going on here. I don't have any square roots for negative values. They're complex numbers. They're not real numbers. I don't quite like how this looks. Let me make it a little neater. Yeah, that didn't change much. Oh well. So because the domain of the original function is not all real numbers, and the range of the original function is not all real numbers, you do have to be careful with the domain and the range of the transformed function. So if I go back to the previous example, and actually your homework questions will ask you for that, the domain, let's go back here, the domain of this guy, domain of function h, is all real numbers, because the domain of the original absolute value is all real numbers. I can plug in any value. So if I shift stuff around, it's still going to be all real numbers that could be plugged in. Range, however, changes. The range of the original was not all real numbers. The range of the original absolute value function are all the non-negative numbers, right? Because we see here that only function values only exist at the positive and the 0, nothing at the negative. But when we move stuff around, we have to be a little more careful. The range is affected by the vertical shift in this case. So the vertical shift makes us go up 2. So the new range is going to be, and we could see it from the graph even easier, we now can start at 2 and go to infinity for the new range here, because there's no values, no function values below 2 there. Here, both the domain and the range are affected. And we can also, again, based on the graph, be able to figure those out. So the domain of G, it's not going to be all real numbers because the original function is not all real numbers. And from the graph, we can see, well, where do our x values start? Our x values start now at +3 because everything got moved 3 units to the right. Instead of starting at 0, it's going to start at 3 for the domain and go all the way to infinity. So that's why I said below 3 is a little bit strange of a wording, because below would kind of mean below as in a range or something like that. But if you're talking about the domain, then yeah, domain is everything which is not below but greater than 3. So the domain here is 3 to infinity, including the 3. And for the range, that also is now changed, because before the range was not all real numbers. The range for square root function is the positive and the 0. So non-negative values. And here everything got moved 4 units down. So I see that as far as my y values go, there is nothing below this line. So my function values are only above 4, or at 4 it also has a function value, rather -4. So then -4 to infinity would be the range here. All right, so let's keep moving and introduce other kinds of transformations. So the first two are vertical and horizontal shift. The next two are vertical and horizontal. So the book differentiates between stretch versus shrink. I kind of prefer to kind of put them as the same transformation. So let's see how that will work out. I'm going to call them vertical flex, and then horizontal flex. And flex, again, flex can be stretched out or shrank, right? So that word to me means it could go either way. So for vertical flex, we have the following version. We're going to introduce some letter A, which again we're going to say is positive value. And we're going to say that a graph of y equals a times f of x will have a vertical flex by a factor of a units. And I want to spend a little bit of time kind of explaining what does that mean, vertical flex. So if we have a point, for example, our original point on f of x was 2, 5, let's say, and we are applying a vertical flex by a factor of 3. Then for the same x value, there's going to be a different y value, right? The x value is not going to change. If I plug in 2, it's still getting plugged in as 2, so the x value will remain 2. But the new y value will change. If before it was 5, which was f of 2, right? This tells me that f of 2 is 5. Now I'm doing a new value 3 times f of 2. So that's what a vertical flex by a factor of a means. So in this case, it's 3 times 5, which would make our new y value in this case, 3 times 5 is 15. If on the other hand, my a is less than 1, and I'm multiplying by a value less than 1, then it'll make my value, my new y value, smaller. So if I had a point, let's say -3.6 or something like that, and I'm applying a vertical flex of a half to my function, then again, my x value doesn't change. For that point, my x value would still remain -3. But as I would plug it in, this tells me that the original y value, f of x is the original y value, that gets multiplied by a half. 6 times 1/2 would give me 3. And you can kind of see that based on what your a is. If your a is greater than 1, then this flex becomes a stretch. If a is less than 1, then this flex becomes a shrink. Shrunk, I don't know, compressed. So I'm just going to refer to them as flex, and then depending on the value of a, you'll see that they can get stretched out or shrunk. So that's vertical. Horizontal is a little bit different. They always are. So for horizontal, again, I'm going to call it flex. We're going to use a letter B to denote that. B is still positive. So then I have the following: y equals f of bx. So now the factor is inside your function. That's how you know it'll be a horizontal flex, as opposed to a being outside. That would be a vertical flex. So here what will happen is, let's see, how did I phrase it? Vertical flex by a factor. So here it'll be a horizontal flex by a factor of, and here's the difference, 1 over b. It's a horizontal flex by a factor of 1 over b. Now, I'm not going to go into too much details as to why that's the case, but basically to get back to your point, well, let me see if it'll make sense. Let me try to write it. So if I, for example, have an original point of 2, 3, and I apply a horizontal flex of y equals f of 2x, then for me to know where this point is located, I would have to plug in, let me see if this will make sense. So I would need to plug in half of the original point, right? Because if I plug in 1 for my x value, this would be f of 2 times 1, which would give me f of 2, and we know what f of 2 is. So I would need to plug in half of the original x value to maintain that same y value. So I don't know if that made too much sense, but it basically works in the opposite way, similar to how if you add or subtract, it works opposite for when you're inside the function. Same for your horizontal flex factor, it's 1 over b, it's the reciprocal. Right, so then the new point would have been 1, 3. But again, just remember that it's 1 over b for the horizontal flex. And because of that, actually, that's something probably I should have written here for the vertical flex as well. So we'll mention it down here. Because of that, if your value of b is greater than 1, then you're actually multiplying by 1 over something greater than 1. So you're going to get horizontal shrink or horizontal compression. And if your b is less than 1, then something like a half. So if you're multiplying by 1 over 1/2, we know that that's the same thing as 1 times the reciprocal. So if your b is less than 1, then you get a horizontal stretch. All right, so
Professor, can you explain the part about the reciprocal situation again? I didn't really catch that.
Yeah, let me try to write it. If I have the following, if I have y equals f times 2x versus y equals f times, let's say, 1/3 x, right? So in this case, my b is equal to 2. In this case, my b is equal to 1/3. Because they're inside the function, I know that this is a horizontal flex by a factor of 1 over b. So that's important to remember, that it's not a horizontal flex by a factor of b, but instead it's 1 over b. So what will happen here is my x values are going to be multiplied by 1/2. So times 1 over 2. That'll be my horizontal flex. And if I'm multiplying by 1/2, numbers become smaller. Whereas here, if my b was 1/3, then I'm going to be multiplying by 1 over 1/3. And we know that 1 over a fraction, or division by a fraction, is equivalent to multiplication by its reciprocal. It's 1 times 3 over 1, which is 3. So here I'm going to be multiplying by a factor of 3, which will make our values larger. So that's a little bit of explanation on that, and perhaps on an example it'll become a little clearer when we do an actual example on the graph. So first, let's do a vertical stretch. So number 3, we will graph, let's call it g of x equals, so we've done absolute value, we've done square root, let's do a cube root. So we will have 2 times cube root of x plus 1 minus, or let's do plus 3. So this will be our function. Again, we know a few different transformations. We know that there's going to be horizontal shift. We know there's going to be vertical shift. And we know that there's going to be a vertical stretch because the 2's outside. If I had something inside, like a factor here, that would make things a little more difficult. And you're not actually going to get too many of those yet. So we don't have one here. We only have vertical. Now, the order in which we would apply these would matter. And let's think about that. So if I am transforming my parent function of cube root of x, we'll have to remember what that looks like. My first step here, if I say my first step is to, for example, let me think, how can I break it? So let's say I say my first step is to replace x with x plus 1. Then let's say my second step, I do add 3 to the new function. And then let's say my third step, I say, well, let's multiply the new function by 2. Let's see what that would give us. If I multiply the new function, which is this guy here, by 2, then I would get something that I'm not trying to get. I would have to multiply the whole thing by 2, and this 3 would also get the 2 distributed to it, and that would not give me the function that I'm trying to graph. It would give me a plus 6. So here the order does start to matter. If you apply these transformations in a different order, you're not getting your correct result. So if I do my horizontal shift first, my vertical shift second, and then my vertical stretch or flex third, I'm not getting the correct result. I have to do it differently in order to get the function that I'm after. So these pieces are gone. I have to next apply the vertical stretch or vertical flex. I have to multiply this new function by 2. This would give me 2 times cube root of x plus 1. And as the last step, which I already made a note of, that the vertical shift should always be the last step, now I can add 3 to the previous version. So this would be my order of transformations, and that does give me the function that I'm after. So the first step, you're gonna have to do 1 unit to the left. The second step is you're going to apply a vertical flex, I'll call it vertical flex, by a factor of 2. Remember, vertical flex is not 1 over, it is that number. And then lastly, 3 up. Do it in different color. 3 up. So go ahead and try to apply those transformations, and then we will go over and make sure that we got it right. So take about 5 minutes. All right, so before we go over this example, I think that if I write these transformations in terms of what happens to an ordered pair, it might make a little more sense perhaps, or at least might help you a little bit. So let's go back to the first transformation here, vertical shift. So this tells me if I have the original ordered pair, which we will call x comma y, and I apply a vertical shift to it of k units, then my new point is going to maintain the same x coordinate, but the y coordinate is going to get changed. It's going to be plus or minus whatever was, if it's plus k or minus k, the y coordinate is going to be plus or minus k. If I talk about the horizontal shift, then if I have a point x comma y, and I apply this horizontal shift to it of h units, then my new coordinate is going to be x plus or minus h, and then the y will stay the same. But here you have to be careful, right? Because if for k, if it was, maybe I should have split it as two different ones, but I'm not going to. So what I'll do instead is I'll write minus plus, and then hopefully you'll recognize what that means. So this will be minus plus. So if we have minus h, then we go to the right. If we have plus h, then we would go to the left. When we introduce vertical flex, then an ordered pair x comma y is going to keep the x value because it's a vertical flex. So the x value is staying the same, but the y value is getting multiplied by a factor of a. Factor of a. Whereas if we have a horizontal flex, then the y value would remain the same, but x would get multiplied by a factor of 1 over b. So that's important to remember. All right, so now let's get back to this example. We already described our transformations. Let's go ahead and apply them. So I'll start by plotting cube root of x. Cube root of x, the parent function, has points at 0, 0, 1, 1, and also we can mark the point 8, 2. Cube root of 8 is 2, so 1, 2, 3, 4, 5, 6, 7, 8. And cube roots are defined for negative values as well, so at -1, -1, and at -8 is -2. If we were to connect the graph, it would look something like this, extending in both directions forever. Domain and range of a cube root is all real numbers. But I'm going to keep just the points and then start the movement. So first, let's apply 1 left. Each point moves 1 value, 1 unit rather, to the left. Then we have a vertical flex by 2. So again, what this means, a vertical flex by 2, is that the y value of every point is going to get multiplied by this factor of 2. Only the y value. So the x values are staying the same. My point here, the y value is -2. -2 times 2 is -4. So I'm not shifting this point 2 units down. I'm multiplying it by a factor of 2. So this point is now here. But you see how it didn't move anywhere horizontally. It stayed. The y value here is -1. -1 times 2 is -2. The y value is 0. 0 times 2 is still 0. The y value is 1. 1 times 2. 2 times 2 is 4. So again, if we connect these points, we see that the difference between what we had here for the blue guy, which was that, versus what we now have for the green guy, which is that we stretched out vertically, right? So we flexed by a factor of 2. That's what that transformation does. But there's still one more transformation, which is why, again, color coding it can be helpful, because if these were all just points of the same color, you would kind of lose track as to what's where. Probably I would. So the last transformation is 3 units up. So now each of these green points is going 3 units up, not getting multiplied by a factor of 3, but just adding 3 to their y value. So this guy goes up here. It's too big. This guy goes up here. This guy, 1, 2, 3. This guy, 1, 2, 3. And this guy, 1, 2, 3. And this should be now the final version of my graph. If I connect them nicely, then that's what I should get. And it's always a good idea, at least mentally or just sort of for checking purpose, plug in one of the points, maybe this guy, and make sure that it actually works out. For example, I know that the x-coordinate of that point is 0. So let's go and find what is g of 0 and see if it corresponds. If it does, that means we're probably okay, not necessarily, but probably. But if we don't get that point, then I will have to go back and check my work. So this is 2 cube root of 0 plus 1 plus 3. So it's 2 cube root of 1 plus 3, 2 times 1. So that will give me 5. Let's see, 1, 2, 3, 4, 5. So that point corresponds. You could check a couple of other points just to kind of make yourself more sure that you didn't make a mistake. But we're going to say that this is it. This is our graph here. Questions on that part? No? Can you guys hear me?
Yeah.
Yes.
All right, so no questions then.
No.
All right, then let's give you a problem with a vertical flex, with a horizontal flex as well. Let's make something up. Let me see if the book has something interesting that I want to use. They don't have too many of vertical flex, so we'll just make something up. Let's say we have f of x equals, and we'll do a square root in this case. We'll do square root of 2x minus 3. Let me see if I want to make it more difficult or if I'm okay with that. Well, the book doesn't seem to give you the more difficult ones, so I'm gonna refrain from doing that as well for now. Yeah, so we'll just do this one. Go ahead and I'll give you guys a little bit of time to try and graph it. I'll just start you up in the right direction. I would start by saying parent function is the square root function, and we would then do our transformations in the following order. We would first replace x with 2x, and then we would subtract 3 from the resulting function. Now what you have to remember is this guy, this 2 inside a function, means you have to have a horizontal flex by a factor of 1 over 2. So this will be the horizontal factor. And then this guy is going to be vertical shift 3 units down. So go ahead and see if you can transform your points correctly. And I'll give you guys about 5 minutes and then I'll go over it. All right, so let me address a couple of questions here. Somebody asked, how do we understand vertical flex or horizontal? So that depends on where the coefficient is. For a vertical flex, the coefficient is outside of your function, a times the function, so it would be a times the absolute value or a times the cube root, whereas horizontal, the multiplier is inside the function, so it would be like a square root of 4x or absolute value of 2x as opposed to 2 times the absolute value of x. So that's how you tell apart vertical versus horizontal. And then we have, for example, number 3, green dots. Did you multiply y value by 2? Uh-oh, I think my program stopped moving. Let me see if it'll crash or if it'll reset itself. Okay, now it's moving again. So for example, number 3, the green dots were multiplied by 2. So I did not add 2 or subtract 2, I multiplied by 2, right? So this guy for the blue dot, here the point was -8 comma 2, and then what I did is I multiplied the y, or -8, -2 I should say. What I did is I multiplied the y value by a factor of 2, giving me a new point, -8, -4. So that's what we did there, but multiplied by a factor of 2. For number 4, however, this multiplication factor is inside, right? This 2 is inside the function, which tells me it's a horizontal flex. And we know that horizontal flex is by a factor of 1 over, in this case, 2. So when we apply it, let's see how that would look. You can always do more than 3 points if you feel the need to do so. My parent graph, square root of x, I have these points. And I can also do 9, 3. So 1, 2, 3, 4, 5, wait, 4, 5, 6, 7, 8, 9, 3, like that. And first I would apply the horizontal flex by a factor of 1/2. So that means my x coordinates, because it's horizontal, are getting multiplied by 1 over 2. The x coordinate for my first point is 0. 0 times 1 over 2 is still going to be 0. Here x coordinate is 1. If I multiply it by 1 over 2, I'm going to get a new point. So let me write that one down. The original point was 1, 1, right? When I multiply it by 1 over 2 for the x coordinate, I'm going to get 1/2, 1. So that's where the new point is. 1/2, 1 is right around here. Then I had a point of 4, 2. When I multiply this guy by half, x coordinate, I'm going to get 2, 2. So that would be a point here. The 0, 0 is going to remain 0, 0. That one wasn't fun. Then I had 9, 3. When I multiplied by a half, 9 over 2, which is 4.5, 3. So this point will go to about 4.5, 3. And we can keep going. Like if I had a 16 in there, if I marked another point, 16, I know it would be at 4 for the original. For my new point, it would be 16 times a half is 8. 8, 4 would be a new point there. So 8, 4 would be a point right here. So we see we still maintain the general shape, but the function kind of got squished horizontally in this case. But that's not my final answer. So we still have to remember that was just one of the 2 transformations. I would still then have to apply the final transformation, which is a vertical shift of 3 units down, because I have a -3 in there. So I'm going to get rid of the line. and move each point 3 units down. Gets a little messy, but we'll do our best. So this would be my final version here. All right, so these are the vertical and horizontal flexes. Now, the last type of transformation that we will see, oh, and by the way, before I do the last type, notice that if this would have been 1/2 instead of 2x, so if the coefficient was 1/2, then we would have a horizontal flex by 1/1/2, which is a horizontal flex by 2. So instead of dividing my x values by 2, I would be multiplying them by 2, and that would stretch out my graph compared to the original one that is getting sort of compressed. All right. So the last two types of transformations are reflections. Let's try this again. Reflection. And we'll first do reflection about the x-axis. And we're going to say y equals negative f of x is the reflection around the x-axis. And as far as ordered pair goes, if I have a point x comma y, and I apply this reflection, the new point would be x would stay, and only the y value would get moved over. So x comma negative y. That's the reflection about the x-axis, because again, if we have, let's do a little picture. If we have our coordinate graph and I have some point up here, if I want to reflect it about the x-axis, that means I would go down to the line of the reflection, which in this case is the x-axis, and then same distance past the line of the reflection, which would yield me a new point. So when we have reflection about x-axis, that means that the 2 points are symmetric about the x-axis, which is the line of the reflection here. Reflection about the y-axis would be y equals f of negative x. So again, when we have a negative outside, whenever something's outside of the function, it's always associated with vertical. Whenever something that changes inside the function, like in this case, then it'll be associated with horizontal movement. And horizontal movement in this case is reflection about the y-axis. So on an ordered pair, the original point x comma y would get transformed, where it's now negative x comma y. And if we do that little graph to show what it looks like, if I have the original point anywhere, then the line of the reflection is the y-axis, so I would go towards the y-axis, then the same distance past the y-axis, and that would give me my reflected point like that. So here we only have reflection about x-axis and reflection about y-axis. No reflection about the origin in this case, in these two cases. So these are our reflections, and you can tell how this is again outside. So this is up down, vertical movement. This is inside, so this is left right, horizontal movement. All right, so now we have all the transformations in place. I will do just one more example on this topic, and then continue on. So let me pick something difficult. Let's make this number 5, I guess. And we will call this g of x equals, and we'll put a bunch of things in here. So we'll do, I don't know if it'll be too complicated. I don't want to make it too complicated because the book doesn't give you overly difficult examples. So we'll keep it normal. We will do 3 square root of 1 minus x plus 2. So this isn't easy. This is not an easy example, and there's a good chance that if you try it, you'll get it wrong on the first go. But I still want you to try it first. So from scratch, try this one. I'll give you probably a little more than 5 minutes. See how far you can get. There is quite a few transformations here, right? There is this guy, there's this guy, this guy, this guy. So everything you have to more or less pay attention to, and also figure out the proper order in which to do it. And then we'll go over it. All right, guys. So again, this one is not an easy one. I would not give you something like that on a test. For the homework, it's fine. You have time. But there's two ways you would be able to get this one started. Or there's definitely more than two ways, but there's probably two of the easier ways to get this one started. One way is to factor out a negative, and that's actually some strategy that we will see if we have a horizontal flex along with a horizontal shift. We would need to factor out from the inside of the function. In this case, it's just an option, so we could have factored out a negative like that, and then it would give us a x minus 1 and then the plus 2. But that's not the option I would go with here because I haven't done an example like that yet. So instead, we would do what was mentioned in the chat, is we can just change their order. We could put negative x plus 1, and then we have plus 2. So that is the option that I will go with. Now, our parent function here is the square root function, but we have a lot of transformations. So let's see if we can keep track of them and also their order, because now let's see what happens. If I, for example, first say that let's change x with x plus 1, actually the other way around, this is the correct way. So let's say I first say let's change x with negative x. And then at the next step, I would say let's exchange x with x plus 1. Then that would give me the following result, right? If I replace x with x plus 1, I would have negative times the new x, or x plus 1. And if I distribute that negative sign, I am not getting the original version of the function. I'm getting a negative x and a negative 1. That's not what I want. So for that reason, it's important to maintain the correct order here, which is to first replace x with x plus 1. So I get that. Then replace x with negative x. So I get that. Then multiply the function by 3. I get that. And finally, last, the vertical shift, add 2 to the function. So 4 steps here that we're going to have to do, and also we'll try and be careful about them. So let's see. First step is going to be the plus 1. This is 1 unit to the left. Then replace x with negative x. That is a reflection. And which reflection would that be? Would that be reflection about the x-axis or the reflection about the y-axis? So this would be that guy, right? This would be a reflection about the y-axis because the negative sign is inside of the function. So this is reflection about y-axis. Then I have times 3 outside of the function. Again, times 3 outside of the function means I am doing a vertical flex by a factor of 3. And finally, plus 2. That tells me I am going, I don't think I have any more colors to use here. Let's see, can I do more colors? I guess I can do purple. So I can do a vertical. Well, I'm not going to say vertical, I'm just going to say 2 up. All right, so those are all the transformations that will need to take place. So this could get pretty messy, but we'll try and keep track of it. All right, so first we'll mark our points for the parent function, the square root of x. And I'll just do with 3 points. So these are my parent function points. Next, I have 1 unit to the left that we will mark in blue. So each point is going 1 left, 1 left, 1 left. Okay. Then the reflection about the y-axis. So that means whatever my point is located, it has to jump to the other side of the y-axis. If it's already on the y-axis, it's going to stay there. So this point is going to go here, right? It goes across the y-axis, it acts like a mirror, and it reflects it, so it goes over here. Or if you prefer to go with coordinates, the original coordinates were -1, 0, so now they're +1, 0. This stays, and this, the original coordinate, would be 3 for the x value, so now it's going to go as -3 for the x value. So that was the reflection step in green, reflection about the y-axis. If we were reflecting about x-axis, then the points will go up or down depending on where they are. So here it's left or right depending on where they are. They go across the line of the reflection. Next we have vertical flex. Oh, I already used red color. Vertical flex by a factor of 3. So let me think what color I can use here. I have light blue or something like that. See if that will work. So this is vertical flex by a factor of 3. So now my y values are getting multiplied by 3. The original y value, and we're looking at green points, the last set were green points. So here the y value is 2. 2 times 3 will give me 6. 3, 4, 5, 6. So this point is up here. 1 times 3 is 3. 0 times 3 stays. And finally, my last step is 2 units up. So all of my points should go up 2 units. My blue points were the last set. So this guy goes up 2, this guy goes up 2, this guy goes up 2. And my general shape is preserved. So this is what I should have. Now I do want to check at least this point and see if it works out, because if it doesn't, that means I have a mistake somewhere. So let's at least check one of the points, or maybe a couple. So I know that g of 0 should come out to be 1, 2, 3, 4, 5, it seems. Let's check if it works out. I have 3 times the square root of 1 minus 0 plus 2. So that's 3 square root of 1. That's 3 plus 2, 5. So that one works out. That point is indeed 0, 5. Let's maybe check one more point. Let's check this guy out. The point here is 1, 2. Let's see if we get that. G of 1, 3, square root of 1 minus 1 plus 2, square root of 0. That's 0. So we got that. So again, it's not necessarily that everything is correct, but at least it gives me a little bit of peace of mind that what we have is good. what we have is correct. So this would be our final version here. All right, so this will be it for our 2.5 lesson. We will take a break. We'll do about 15 minutes for a break, so it's 8:40. We're gonna start back up at 8:55. Ooh, what did I do here? So 8:55, we're going to continue on with our 3.1 lesson. All right, guys. So we probably need another 30 minutes or so of lecture. Still doing 3-1. And 3-1 is properties of linear functions. And we introduced various properties of functions. Now we're going to be a little more specific for a couple of lessons. We'll do linear and we'll do quadratic functions, but today just linear. So a linear function is a function that can be written in the form f of x equals mx plus b, where m is a coefficient, a constant, and b is also a constant. So m represents the slope and b is the y-intercept, specifically the point 0, b. We know that the graph of any linear function is always going to be a line. So we will say graph of any linear function is a line, hence the name linear. And something that is not a linear function or called nonlinear, the graph then would not be a line. And again, then the slope of the line is m, and the y-intercept of the line is the point 0, b. And we also remember some of the things from before when we talked about a graph is said to be increasing or decreasing or constant. For linear functions, we can determine that just by looking at the slope. So if the slope is positive, that tells me that the function is increasing. If the slope is negative, that tells me that the function is decreasing. And if there is zero slope or horizontal line, that tells me the function is constant. In general, for functions, it could change from increasing to decreasing on different intervals, but for lines, it stays the same throughout the entire domain. Because if a function is linear and has a slope, the slope doesn't change. Therefore, if the slope is positive, it's always going to be increasing on the entire domain. If the slope is negative, it's always going to be decreasing for the entire domain. Now, we had a part that I think I told you to kind of look over on your own back in, I think it was 2.2 when we were talking about properties of functions, which was called the average rate of change. So now we can look back at that a little bit. Average rate of change. We're going to define it. So when we talk about average rate of change of a function, we'll give it a name f, and we have to specify where we're looking at that average rate of change between some 2 points. So average rate of a function f between 2 points we'll call them x1, x sub 1, and x sub 2, is given by the following formula. So this is in general for any function, not just for linear function, but for any function f. The rate of change is defined as, the average rate of change is defined as change in y over change in x. The symbol for change is delta. So delta y over delta x, triangle basically, is delta. And we know that y are the function values. So the change in the function values would be f of x sub 2 minus f of x sub 1 over the change in the x values, which would be x sub 2 minus x sub 1. So this is what we refer to as the average rate of change for any function f. Now for a linear function, this average rate of change is special. And we have a theorem which we're going to state. We're going to state that average rate of change of a linear function and again, linear function can be given of the form f of x equals mx plus b is always m. So regardless of what type of a linear function you have, the average rate of change for any linear function is always the slope of that linear function. And we're actually going to prove this theorem because it's a very basic proof, so it's worth mentioning. So let's do a proof on the next page. So basically this theorem tells us that if we have a linear function, the average rate of change between any 2 points will always be the same, specifically m, the slope of that linear function. So the proof for that theorem looks like this. We start by saying that we have a linear function, general form, f of x equals mx plus b, or rather it's called the function form, but again, we're using arbitrary m and b, not a specific value. Then we know that the average rate of change is defined in the following way. It's f of x sub 2 minus f of x sub 1 over the difference, x sub 2 minus x sub 1. But because we have a specific function here, linear, we can plug in x sub 2 to get the following. So f of x sub 2 is equal to m x sub 2 plus b minus f of x sub 1 is equal to m x sub 1 plus b over x sub 2 minus x sub 1. And then through some algebraic manipulation, we'll be able to show that this whole thing equals m. Distribute the negative sign. That would make it negative mx sub 1 minus b now over x sub 2 minus x sub 1 plus b minus b cancel in the numerator, leaving us with mx sub 2 minus mx sub 1 over x sub 2 minus x sub 1. Factorization, factor out the GCF m in the numerator. And the denominator is already that. I'm just going to put in parentheses to group it and to show that we have the same factor x sub 2 minus x sub 1. So as long as x sub 2 and x sub 1 are not the same point, they're two different x values, then these will reduce, leaving us with just m. And that's exactly what we were trying to show, that this guy, the average rate of change for any linear function, is always the slope of that function. So that's the proof. All right, so let's see what type of examples we can do here. We will start with number 18. Few parts to this question. We're given h of x defined as -2/3 x plus 4. Part A is asking us to find the slope and the y-intercept. So we identify that this is a linear function because of the format. It's mx plus b. And from here we can tell that the slope, m, is just the coefficient, -2/3, and the y-intercept is the point 0, +4. So that would be part A. Part B is asking us to graph. Here you might have to remember a little bit of algebra. I'm not going to do a very neat graph. I'll just kind of sketch it. But if we have slope-intercept form, in algebra we talked about a few different methods for graphing lines. One of them was from the slope-intercept form. So if we do that, we would first plot the y-intercept, which in our case is 0, 4. So 1, 2, 3, 4 on the y-axis. And then we can use the slope, and we have a couple of options for the slope, right? If it's -2/3, that means I can either use -2/3, or I can use +2 over -3. Both are, well, all three of them are equivalent. All three of them are equal. So it doesn't matter which one I use. I'll use this guy. So that tells me the rise is -2. So I'm going to go 2 down. And the run is 3. So I'm going to go 3 to the right. And that gives me my second point. If I connect these with a line, then that will be my graph of the line. So that's one approach we have for graphing lines, just by using the slope-intercept form. And we could see if I used +2 over -3, especially if my scale was correct, that would have given me a same point on the line. I would have gone up 2 and 3 to the left, so that will give me also a point on this line. So that would be the graph using the slope and the y-intercept. Part C here is asking us what is the average rate of change of this function. So what is the average rate of change for this function f? And here we could either do it the long way by picking 2 points, and especially because we aren't even given 2 points, we have to realize that this is the theorem we're going to use here, that anytime we're looking for average rate of change for any linear function, it's always the slope. And since we already know the slope, then the average rate of change here is exactly that. We don't even need to do any calculations. We already know what the slope is. So that's what that theorem tells us. Because if you guys did your homework, you had to find average rate of change for some nonlinear functions given 2 values, and then you have to plug them in and actually do some calculations, whereas here you don't need to do any calculations. You already know the slope because this is linear. Part D is asking us whether this is increasing, decreasing, or constant. And again, remember, this is linear, so it's a special approach. We don't need to consider any specific interval. Just based off the slope, we can conclude that this is a decreasing function on the entire domain because the slope is negative. So yeah, that was the page here. Negative slope tells us decreasing. And we can see it from the graph that any, from left to right, this is always falling regardless of which interval I consider. So this makes sense, it's decreasing. So you'll have a couple of examples like that. Careful if you run into something that has a slope of 0. Make sure you remember how to identify slope 0. It's just a horizontal line. The more interesting part on this section is dealing with with functions, and then also being able to read off not just from the function notation, but also from the graphing notation. So we'll do 2 examples, and I think that'll, maybe 3 examples, and I think that'll be it. So for number 30, we have actual function defined for us. We have f of x is defined as a linear function 3x plus 5. And we have g of x is also defined as a linear function of negative 2x plus 15. And then we have various parts of this question. Part A asks us to solve the equation f of x equals 0. So here everything is algebraic, but we want to kind of pay attention to things, and we want to notice how these solutions are going to look like, so that if we're given a graph instead of the actual algebraic definition, we can still understand and get those solutions from the graph. So if we say f of x is equal to 0, algebraically that just means we have to solve the equation when the function f of x, which is 3x plus 5, is equal to 0. So this is just solving a linear equation. Subtract 5 on both sides, divide by 3. But let's understand something. What we're asked here is to find when is the function value equal to 0. So basically the question is, at what input, at what x value is the function equal to 0? And then the answer is that x input, it's a single input, x equals, and we found it to be negative 5/3. For part B, now we want to solve an inequality. When is f of x strictly less than 0? So here we're saying, well, for what input of x are my function values, are my y values strictly less than 0 or negative, right? Less than 0 means negative. Algebraically, that just means I want to solve an inequality. 3x plus 5 is less than 0, which again, we should easily be able to solve. Subtract 5 on both sides, divide by 3. X is less than negative 5/3, and we want to write our answer in an interval notation because this is describing not a single x value, but infinitely many x values that are negative infinity up to negative 5/3. For all of those values, our function value will be less than 0. Our function value would be negative. So again, it's an interval for the x values. For part C, we're asked to solve f of x equals g of x equation. And again, this is algebraic, so we would just plug in our f of x, and we would plug in our g of x, and this is a linear equation in one variable, so we would move 2x to the other side, so that would be 5x. We would subtract 5 on both sides. That would be 15 minus 5 is 10. So x equals 2. Now, soon in our next example, we will have a graph. And on that graph, we will have graphs of f and graphs of g. And it'll say, well, when is f of x equal to g of x? So this will be asking us, well, when are their y values the same? Or at which points do these graphs intersect? But the solution will be the input, the x. So at which x's do these functions basically intersect each other if we have a graph to look at? The next part is D, which is an inequality now. When is f of x greater than or equal to g of x? And again, this is all algebraic approach for now. So we would say, well, when is 3x plus 5 greater than or equal to negative 2x plus 15? So we would solve it very similar to how we solved the equation. We would get 5x greater than or equal to 10, or x is greater than or equal to 2. Again, this is an interval. This describes an interval for all x's that are 2 or more. So we would use the interval notation to denote that. So x's are from 2, including the 2, all the way to infinity. Part E here asks us to graph. And perhaps it is a good idea to do a graph, but we will have to go to graph paper for that, because these have to be pretty exact, otherwise it won't work. So I'm going to do that here. Again, let's write down the two equations that we had. This is number 30. First equation, f of x was 3x plus 5. Second equation, g of x was negative 2x plus 15. All right, so let's try and graph them. And 15 is a pretty big number, so I'll start down here somewhere. Hopefully that gives me enough room. All right, so for the first graph, we will plot the y-intercept of 5. We will use the slope of 3. All right, so on this guy, slope is 3 or 3 over 1, and the y-intercept is 0, 5. So I would go up 3 and 1 to the right, connect them. And if we do everything correctly, everything will line up with our algebraic approach. So I'm trying to stay neat here, and let's see if it'll work out. I think I missed. Let's try again. Maybe let me mark a few more points. So up 3, 1 over. So these are my points. Keeps jumping in the last second, but I think this is close enough. All right, for my blue function, my slope here is negative 2. So we will say negative 2 over 1. My y-intercept is 0, 15. So when I plot it, I have to go to 15. So this is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. My slope is 2 over 1, so I have to go down 2 and 1 to the right, negative 2 over 1, so down 2 and 1 to the right. And let's connect these 2 points and a few more. So this will be on the line, this will be on the line. All right, let's see if it worked. So this is my g of x, and this guy is my f of x. Now you'll have to kind of consult your notes. The first question, part A of this, we asked, well, when are f and g equal to each other? Or actually, we asked, when is f of x equal to 0, I believe. That was the first part. So now, based on the graph, we can say, well, when is the function value for function f equal to 0? And if we were careful and close, we would get the correct result, which, let's see, what was it for our I can't really look at it. So what was our answer for that guy when we did it algebraically? It was like -5/3, right? So it's -5/3. That was our answer from before, which is like -1 2/3. So here our function value seems right about correct, right? -1 2/3. So that's where our function value of f, the y value, is 0 at that point when x is, again, we're approximating from the graph. Algebraically we could do it exactly, but from the graph we see that that seems about correct. That point is good. Then we were also asked, I'm not going to do all the parts, but we were also asked to solve the equation f of x equals g of x. So that now graphically tells us, well, when are the two y values for the f and for the g the same? So this is the y value here when they are the same. It occurs at this point. And that point, the x value is 2. That one we can kind of see pretty well. And then we also had to solve one of the inequalities, was when is f of x less than or equal to g of x? So here we're saying, well, when are the y values of function f below the y values of function g? And that occurs at this region, right? This is where f is below g from this point on. And we would have to describe that in an interval notation for the x values. So this occurs out here. Right? This occurs between -infinity and, let's see, did I have that right? F is less than g, so this is f. Yeah, so -infinity up till 2. And hopefully that's what we got on our algebraic approach as well. So again, we have to be able to connect graphs and read off this information from the graphs as well. And that's what our last example is going to be. So our last example, we're going to do 36. And there, again, these are on page 132. I'm going to try and graph it the best that I can, or at least something similar. I might not do the scale exactly, but let's say we have x value, y-axis, x-axis, and we have some points. We have -4, +7. So -4, 1, 2, 3, 4, 5, 6, 7. We have 0, 7. Then we also have 0, -8. 1, 2, 3, 4, 5, 6, 7, 8. Then we have 7, -8. 1, 2, 3, 4, 5, 6. It's probably easier if you look at this in the book, but since I already started, might as well. So we have this line. We have this line. There are two horizontal lines in this case. And we have a line that cuts across them. These 2 points. So these are my coordinate axes, my x, y axis, and then I have the red line is f of x. So the red line is y equals f of x. The green line is g of x. The blue line is h of x. So that's what the question has. And again, I'll mark the points down because it's going to be a little easier. This point here is -4, 7. This point here is 0, 7. This point here is 7, -8. And this point here is 0, -8. And we only have to answer 2 questions here based on the graph. So we don't have any equations given, and of course we can find them out, but we're not even going to do that. We're just going to go off the graph. For part A, we want to say when is f of x equal to g of x, and for part B, we want to say when is, so that one is tricky, when is g of x less than f of x less than or equal to h of x. So you have a compound inequality. I'll give you guys a few minutes, like 5 minutes, let's say, to try and answer these 2 questions based on the graph alone. Again, these will be in terms of x. We're solving for input value for x here. So go ahead and take a few minutes and figure it out. All right, guys, let's look at this one, our last example. Then we got to do a roll call, and then we should be good to go. So, first part, it says f of x is equal to g of x. So we are only looking at the green line and the red line. We don't care about h of x or part A. It's not present. So it's asking us when is the y value, or when is basically function, the graph of function f intersecting the graph of function g, because that's when f of x is equal to g of x, when the two graphs intersect each other. That occurs here at that point. But our solution is not the ordered pair. Just like in the previous example, when we were solving such an equation algebraically, we saw that our solution is simply the x value where the input, or the x value where this intersection occurs. So here the solution would just be x equals 7, and that's it. That would be the solution. If you put 7 comma negative 8, that would be incorrect. It's just x equals 7. For part B, it's a little trickier. It's 3 parts, right? So it's saying when is function f, which is the red guy, when is it greater than function g, but at the same time less than or equal to function h. So first, let's consider just part of this inequality. When is g of x less than f of x, or you can also read it, when is f of x greater than g of x, right? So f of x is the red function, g of x is the green function. F of x is greater than g of x on this part, and it keeps on going, right? So it's, as long as you're to the left of that point, everywhere here, function f is above function g, just looking at part of that inequality. But there's a second part of this inequality. When is function f less than or equal to function h? So function h is the blue line. Again, f is still the red line. So when are the function values of f less than or below h? And including when they're equal. So the equal part is right here, that blue point. And less than would be below. So this guy. So the region where that occurs, when both of those conditions are satisfied, is this region. But remember, to answer our question, we need to state the interval. So the interval where that happens, we're including the blue point, that's included because that inequality is less than or equal to, but we're excluding this point because that inequality is strictly greater than, f of x is strictly greater than g of x. And if we sum this up in interval notation, we would get -4 as the starting point, and that's included, all the way to +7, and that's excluded. So that would be our solution. Again, it takes a little bit of time to kind of see that. You might need to later sit and just redo this example until it makes sense to you. And then hopefully you'll see where those answers came from. If I do it in 5 minutes and it doesn't click right away, that's normal. You might have to sit and decipher your notes and go over them. All right, so that was what I wanted to cover for 3.1. If you run into a supply-demand question, I'm just going to leave that for you to look up on your own. I don't concentrate on the supply-demand questions. I won't test you on those as well. Homework, you can have them, but I'm not going to put them on the test. So I'm going to go for a roll call at this point. And then if there's a couple of short questions, then we can address those as well. So let me set up for a roll call. And let me make sure I save my my notes.
Test, test. Test, 1, 2, 3.
Alrighty. So when I call your name, make sure you guys either reply through your microphone and unmute yourself for that, or type in the chat. Prefer microphones. Soon we're going to need microphones and cameras. Kenya.
Here.
Amr.
Here.
Amanda. Colin.
Here.
Alexander.
Here.
Olivia. Gevorg. And Gevorg Galiban. Thank you. Aranza. Joseph. Lindsay. Annie or Ani. Gregorian. Annie, Gregorian. No, Annie. Chloe. Oh, Annie's here. Chloe's here. MD.
Here.
Susan.
Here.
Roman.
Here.
Jennifer. Jennifer.
Here.
Thank you. Gurgen.
Here.
Oscar.
Here.
Adam.
Here.
Anastasia.
Here.
Oganes. Sareen. Anna. P.
Here.
Anna R.
Here.
Maria.
Here.
Ellen.
Here.
Ross.
Here.
Andres.
Here.
America.
Here.
Susie.
Here.
Suzanne. Oh, got you. Michael.
Here.
Nagetta.
I'm here.
Natalie.
Howdy.
Renee. Darlene.
Here.
Adriana.
Here.
Alan.
Here.
Mateo.
Present. Here.
All right.
What's up? Like,
So let me go over people that I marked absent. There weren't a lot, I think. Are there any? Not that I marked